Hello, everyone. With a great pleasure, I'm going to introduce our colloquium speaker today, Professor Yves Atchade. He is a full professor of statistics in the Department of Mathematics and Statistics in the University of Boston. And he is also a faculty in the computing and data science there. He received his PhD degree from the University of Montreal in the year 2003. And before he joined Boston, he was a faculty at the University of Michigan Ann Arbor, part of the statistics. His research deals mainly with the MCMC method, Bayesian inference, and the development of statistical method for environmental prediction. He is a fellow of IMS, and he is an editorial board member of the HDSR journal, Bernoulli journal, and JAXA. Please join me in welcoming our speaker today.
Thank you, Patricia, for a very kind introduction. It's a pleasure for me to be here. Again, thanks to Patricia for the invitation, and to Judith for streamlining everything. Thank you. My talk today is about learning to solve inverse problem, and this is part of a bigger project that we've been working on, that I'm not going to talk about particularly in much detail. So but the idea is to try to combine satellite measurement and ground measurement to do better environmental and weather prediction in West Africa. And as part of that, there's a lot of methodological questions, a lot of theoretical questions that comes out of it that I'm also very interested in addressing, and that's the topic of the talk. And it's jointly with former and present PhD student and collaborators. So without further ado, and by the way, if you have any questions, and feel free to interrupt. I'll be happy to take questions. It's gonna present the framework, and of course, inverse problems are very well known. Statistics itself can be framed as an inverse problem. The language that I'm going to use here is looking at X as the quantity of interest, and for us, X will often be an image, but here I'll write it as a nx dimensional vector, and X is related to a measurement that we have, and that is Y, and this is happening, and we believe that the observation is coming to us through this distribution assumption that we're making here, that is typically called the forward model. And the goal is to reconstruct X given Y. In general, something I should say is that the dimension of X, it's often larger or comparable to the dimension of Y, and it's not clear, even when we understand the forward process as a model. There's a lot of loss of information going from X to Y, and going back from Y to X is often ill-posed, and you don't have easily ways to reconstruct the original signal. So in that kind of setting, it is really key to have additional information on the distribution of X. And if, for example, I believe that the prior distribution or well, I should say the marginal distribution, and here I'm going to make the distinction between the prior and the marginal in the sense that when I say marginal, I really mean that there is some distribution under which that has generated the X, whereas if I say prior is something that as a modeler, I'm actually assuming that X is coming from. So if, and the reason I'm making that distinction will hopefully will become clear later. So if P0 here is the marginal distribution of X, then the conditional distribution of X given Y would come out this way, and this would be really the object of interest. You could want this, or you could want the frequentist version of it. That takes the mode of that distribution. And typically when we do inverse problem, this is really what we do. And the goal here is because P0 is not known, you know, you have to make some assumption of what P0 is. And it's the difficulty of implementing something that, you know, this very straightforward step that I wrote here is really particularly trying to formalize what P0 is and come up with a good model, good approximation for P0 in order to get the posterior distribution that you will use. So and then of course, and there lies the challenges of trying to solve this inverse problem is that you really need to have a good understanding of what is the marginal distribution that the data is coming from, and then implement that. And it could also be the case that the forward map is not known. And even if you have these two, I'm trying to evaluate this and trying to solve this minimization problem could be costly. And in particular context that we are working on, as I said earlier, we have satellite measurement, and you need to solve this inverse problem for each one of the pixels. And if the number of pixels is very, very large, then the number of those admin problems that you need to solve could be also very large. What we look into is another way to approach the problem where we try to learn directly the this is a little bit not super intuitive. So we try to learn directly the function g in a non-parametric way using data. So in other words, the goal is to learn to solve the inverse problem. So I'm going to learn g, and now once I estimate g as a function, if you give me a new image y, I just compute g of y, and that will give me the x. And that's the main idea of the talk. And the way we also implement this is we take a Bayesian approach to do it. And in the process, we develop some specific approximate MCMC method to deal with this large posterior distribution. And the second part of the talk would be to give you a brief overview of what we did for these approximate MCMC. So that's the plan, that's the agenda for the talk. And if there's no questions, I will jump right into it. I think I'm repeating myself here. So right. So So the setup is, as I said earlier, so we have some inverse problem here where the forward model, now we need to parameterize the forward model here by assuming that there's some parameter theta that it may not be known, describing the forward process. And again, we want to reconstruct the image X. But as I said, the forward process might have some parameters that we may want to also estimate in the process. So here are some, some examples, perhaps that to illustrate the point. In many cases, so you have, you have a linear inverse problem where your image is related to the observation. So, in denoising, deburdening problem, many computational imaging problems are inverse problems where you have some real image X, and but you don't observe it. What you actually see is a blurred version of it. And the blurred version, typically, you can model it as, you don't, the image itself, each pixel is not coming out as it is, but you're getting a weighted average of the image of the pixel and the neighboring pixel, and then the result is completely blurred. Now, once you get the blurred image, how do you reconstruct to get back to the original image is the inverse problem. And, it might be the case that the matrix A that there's the blurring of the difference of the noise is not known, and you also like to estimate that as part of the problem. And this is actually also the similar problem that you have in MRI imaging. It's exactly the same, except that the k-space data that you get from the forward problem is coming from a Fourier transform of the original image X. All right, so the approach that we take into this problem is the following. Suppose now that, well, you don't have one instance of the inverse problem that you're trying to solve, right? So, in all the description that I presented earlier, I was giving you just one instance of the problem where you have one X giving you one Y, and you want to take that Y and try to invert it and get the X. But suppose that, in fact, what you actually observe is a whole bunch of instances of the problem where you have xi, yi, where each one of the pair xi, yi is coming out from the model that I described earlier, where the x is coming from some parallel distribution or some marginal distribution, P0, and given the x, you observe the y, right? So now you have a sort of classical statistical problem where you have observation, and what you would like to do is estimate a quantity, is estimate a function like this, g, that I'm defining here as g hat. Right, so rather, you would like to estimate this, getting confused with my object of interest is this not the hat, but rather the G that it's not written on the slide there, but so one way you could this object is what this object is trying to estimate is replace the theta hat here by the theta star and the p hat by the p0, and that gives you a G, and that's the G that you're trying to estimate. Of course, one thing that you could do is just use your data and not parametrically estimate p0. And also, of course, because y given x is coming from this model, you could also estimate theta star from it. And once you have these two estimates, you plug in, and you could compute this quantity here for each instances of y. But this is can be very cumbersome or very difficult to do, depending on how you model the P0. If you want to do something non-parametric, you get a non-parametric estimator, and then you want to plug it to do optimization. That means that the estimate that you get has to be differentiable. And then you need to be able to work with that derivative in order to turn it in and run a survey on this G. So we're trying to avoid something like that. And estimate G directly. Okay. Does that make sense? Yeah.
P sub 0 prior distribution?
It's not the prior distribution. So what I'm saying is that we have a data where the xi is not is the object of interest. So if you think of one copy x and y, x would be your object of interest, but you don't observe x, but you observe y. So what I'm saying now is that, for example, consider the de Broglie problem. I could go on and collect a data set of, and this is exactly what we did in the example where we take a big database of images of faces of celebrities, and then we blur them. So now we have a bunch of X and corresponding Y. Well, now I want to make a probabilistic modeling for these images that we have, these actual images that we have. Of course, so what I'm saying here that these images are actually coming from some unknown distribution P0. So that's the setup here. So it's not really a prior. So and if I have data, then what I could do is just construct a non-parametric estimate for P0. And once I have that, I could come here and use that to do the inversion. But it would be very cumbersome to do because these are high dimensional images and non-parametric estimator that would be smooth. They are difficult to build in high dimensional setting. Is that clear? Yes.
So the xi is not observed, right?
Yes.
So is it kind of a surrogate variable?
Sorry. So here the xi is actually observed, but if you in the second stage, you will be in a situation where the xi will not be observed. So, example, once I construct my G hat using this data set D, later on I will be presented with a blurred image for which I don't have the real image X, and I would like to unblur it. But to tackle this problem, I'm giving examples of xi and yi, and I'm going to use those examples to construct a way to solve the inverse problem. Yes?
So when you choose the xis, do you take in particular design to select which xis you are going to sample?
That's a good question. We randomly just select them. We have this select, for example, the de Broglie example that I present in a minute. So we just take the select A database and we randomly select from it. Yes.
You have pairs of x and y. So why don't you model x equal y? Because then if you have new images, then you can just problem over.
That's exactly what we did. Yeah, but you could actually do this, right? You could also do what I'm writing here, which is that you would because the P0, the distribution that the x's are coming from, it's a classical problem, right? You have a bunch of data and then you just estimate the distribution that they're coming from, and then I'll give you P0. But you could also estimate this theta star, and once you have these two objects, you will do something like this. And this actually is a lot of literature where people do exactly this. Any other questions? All right. So this is that's exactly what we did, which is that when you look at the mode of that conditional distribution of x given y, there's an interesting question as to how does this conditional distribution of x given y behaves. And you could make the case that if the P0, the marginal distribution of the true images, have a reasonable contraction properties, you could expect this conditional distribution of x given y to actually concentrate around its mode. And if that's the case, an assumption of this sort, where I'm saying now that we can write the xi as a GOY plus a noise, where the noise would be, say, sub-Gaussian, would make sense. But most certainly, most likely, it will not be a mean zero that you have, a conditional mean zero that you have here. But we are going to make the assumption that, in fact, it is mean zero, but it would be not. What would be more realistic would actually make the assumption that this conditional expectation here is small, and make that appear in the analysis. But we did not do that in this work. Okay. And of course, once you get here, and the question of under which condition this happens, it looks a lot like posterior contraction based on posterior construction, but it's not quite, because this framework here, there's a lot of work also when you look at the inverse poem literature, based on inverse poem literature, where people trying to establish results of this type. But here we say something a little bit more, which is that you have a sub-Gaussian, you have a distribution on the noise that is typically not available when you do straightforward contraction analysis. Anyway, so that's the main assumption that we're making. And so when you have this assumption, what this is telling you is that now you could just do a regression of just regress the y on regress x on the y's, and then you will be able to estimate the g. Once you do that, you end up with a jihad, a posterior predictive inversion map that will look like this. And once you're given a new image y, you could just compute this quantity, and that would be your inversion for x. So that's the general idea of what we did. And just to give you a little bit more details on how we did it, we used specifically a function class called the unrolling algorithm unrolling function class that specifically fit the framework of the problem. So let me try to describe that a little bit. First of all, suppose that you take any function class that you want here, GW, for the regression problem that I presented here. This, if you look at this as how your data is distributed, and you want to estimate G, then you could just come up with a function class for G, and then you do a regression. But because the forward map has a parameter f star here that is unknown, then naturally you would like the G to also depends on theta. And so you could, so suppose you come up with a particular function class GW to estimate theta star and G. You could look at it as that you're trying to estimate W, but you have these two forward and backward regression problem where you have the Y given X that comes from the forward problem, and the backward problem is also described by the GW here. And what is interesting here is that you have a situation where you end up estimating both the forward process, which is the forward regression and the backward regression jointly. And you could, and then that will give you a loss function of this sort. You put a prior, and then you end up with a posterior distribution on that. So specifically now, how did we construct this this function? GW. Remember that the function of interest G here is the inverse map. This is a not mean of negative loss coming from negative log likelihood coming from the forward problem plus the marginal distribution. One way to do it is to mimic the way proximal gradient will operate to try to estimate this function G. So one way, so suppose I know the proximal map of the negative log P0. So what you could do to compute G is just do a forward step, just forward gradient based on the F, and then you do a backward proximal step coming from the negative log P0. But of course, we don't know the negative log P0, we don't know the proximal of it. So I'm going to parameterize the proximal of it using a neural network function class, and that gives you an iterate of this form. So if HW was exactly the proximal of the negative log P0, this will give you exactly the proximal gradient, right? And then I'm going to iterate this, say D times, and what comes out of at iteration D is my GW Y of theta. So that's how I'm constructing the function class GW. So I construct the function class really targeting what the function G is, and so there's a really nice interplay here between numerical method and statistical modeling that I'm making use of here, because I have an objective function. The function of interest G that I'm trying to compute has this. I can actually compute it by just running the numerical solver for a very large number of iterations. But now, instead of doing that, I'm gonna use the same principle, right, to build this function class up GW. And the rest of it is really I'm super excited these days about this particular way of doing non-parametric or pseudo-parametric inference, because there's a lot of problems. So particularly in inverse problem where so for example, instead of doing proximal gradient, you could do, people have tried ADMM, or you could even do Markov-Chain Monte Carlo iterations here. You could do really, there's a lot of space here to construct function class based on the idea that the objective function that we're trying to model, we could actually get to it through some numerical method. And the hope is that these function class, all of them give you particular instances of deep neural network, because if you look at what this is doing, this is like a deep neural network where the depth is D times the depth of the HW. So it's a very, very deep neural network function class. And and but the way you construct it is not just by taking some arbitrary deep neural network to try to approximate your function. If you use something that makes use of the structure of the problem. So we analyze this, and if you're interested, here are a couple of papers. This is very popular in the sparse coding literature. Our analysis of it, uses a Bayesian formalism where we put a kind of spike and slap prior on the weight of the neural network, where we construct the spike and slap a little bit differently than usual. So first of all, my prior here, I'm going to call it pi 0, but the way I'm constructing pi 0 is by taking independent Bernoulli distribution and given this Bernoulli random variable, I'm drawing the weight, and then I take a component-wise product of these two objects, and the distribution that I get for this random variable is my prior pi 0. So it's not your it's not exactly classical spike and slap, but the advantage of doing it this way is that you get a lot of convenience in the computation. It may not be, I mean, for practical purpose, you can really consider this as just like your regular spike and slap, where you end up with where you replace this part here by point mass. But normally when you do that, you have to do something else for the computation. But here, you don't necessarily need to worry about that when it comes to the computation. In any case, you end up with a Poisson distribution like this, and then we come up with a particular MCMC, approximate MCMC method to sample from. How much time do I have?
25 minutes.
Okay. All right. So we look at specifically at this particular posterior distribution. So I described earlier. So once you sample from that posterior distribution, you could you have your function class dw. So once you get the w, you could now run your proximal gradient, and that will give you the inverse map G. When we look at the statistical property of that object, we make a specific assumption on the way you could approximate it, because as I said, what the function class is really doing is coming out of the is sort of coming out of proximal gradient descent. So the function HW is really approximating the proximal map of the negative log P0, and here I'm saying that the initial function HW that we're using has the possibility of approximating that. The complexity really comes from these powers. How good the function class is in approximating really comes from these powers here, and particularly from beta 2, the number of the L0 norm of the weight. And what we show is that, in fact, when you, provided that the depth is not too small, you have a rate that looks like this. And the rates really tell us, two things that we think is really useful in practice. The first one is that, in fact, the rate depends on the way that is. You need to have some depth, but it does not need to be very, very large. And but in fact, if you keep increasing the depth of the unrolling that you're doing, at some point the model is going to overfit, and you're going to lose in terms of approximation power. And yeah.
Can you please explain rolling depth and also that notation P?
The Q?
Yeah.
Oh yeah, it's a Q. Yes, yes. So yeah, so
Q and the rolling depth D.
yeah, so the Q, I apologize. So the Q is a P. I use I think in the paper we use Q, but I started the slide here with P, where P is the number of, so when the function HW that you use to approximate the proximal map of the negative log P0, you use a deep neural network to do that. The number of parameters that the deep neural has is P. But in the theorem I wrote Q. P is Q. Q is P. So in the prior that I'm using here, the way I'm constructing the prior is each one of the weight, each one of the component of the weight of that deep neural network. I'm assuming that it has a lambda j that comes from a Bernoulli, but with a very, very small probability of being able to get to 1. And from given that, we assume that the weight itself is coming from this mixture, and this prior construction shows up here. The fact that the prior is actually coming from this point cloud multiplications shows up here, and the depth is so remember that we were building a particular function class to try to model the function G. And the function class that we're building we build it this way by doing proximal gradient descent. But so we do just initialize by some S0, just do gradient descent for forward gradient on using the F, and then of course, we could have just we could keep the two together and just take this guy and shove it here, and just do a gradient on both terms. It's kind of the same, but here we do it backwards. So we do the implicit version of it, where you do the forward and you do implicit on the second term. So we do just regular gradient on this. And then the other one, we do the implicit gradient on it. But you repeat that, say D times. And that gives you a function, because you have your Y in there. And it's the same. So at the end, you have a function of Y. And that's the function that we analyze. Okay. All right. So and what is interesting here is that we have naturally adaptivity here for this function class, in the sense that if the initial function class can approximate the proximal map, if you have a situation where the proximal map has a very simple structure, you could get much better rate. And we have some result where the rate is actually parametric. When the function class can approximate correctly the negative log. So just a few numerical illustration here. So we simulate data. So here, what we're trying to compute is evaluate the elastic net. So this is a really straightforward linear regression with the elastic net prior. And so if this is the problem that we have, where this is a prior for the xi, and this is the way the y are coming from the given xi, then the reverse is the mode is just the elastic net. So what we're trying to do is give me y and then compute the elastic net to get the x. And we want to see how well we can approximate that function. So we apply. So in this particular case, it turns out that this negative log of this term has a very simple structure, and you can construct a deep neural network representation exact to this. So beta is actually 0, and we get the parametric rate in this case. And you could also see in the simulation that as you increase the depth, the method increase, but then further increasing the depth, you lose actually, which is also consistent with the result that we have. We have similar result for deblurring. We apply the method also to a deblurring problem where, again, we take 20,000 random images from the syllable data set and then we blur them. So these images are the x's. We blur them to get the y. The way we blur is by using a Gaussian blurring convolution matrix. And so here we take the HW as in a really standard ReLU convolutional layers. And again, we try to unroll 4, 12, 24. And of course, all these models, they all have the same number of parameters because when we are running, we're using exactly the same HW. And we compare that to actually a much more deeper model, which is off-the-shelf convolutional architecture, which is much deeper than what we do, but it does not actually exploit the forward part of the problem. And we actually get results that completely comparable to this. So this is the result for the much bigger convolutional neural network. And this is the architecture that we're proposing. Again, when you increase the depth, you gain, but increase the depth too much, the model starts to overfit. This is just some random images where we try to apply the method. So this is now images that are not part of the training, but we can still use them to illustrate the method. And you could see that this visually that the depth actually improves a little bit, but at some point you don't get much improvement. And it's also fairly comparable and slightly better, I think, than the last column, which is based on the feed-forward convolutional layer. So this is sort of the end of the first part of the talk. This is there's a lot of questions that still remains open. So first of all, the idea that you could actually estimate, we have a particular data set where we observe xi and yi. What we're doing here is that we were trying to estimate both a forward regression, but also a backward regression, but jointly in the same loss. There's a lot of question as to how well can we do that? And you could imagine, for example, that we may want to also insist on invertibility in the process. So because we have a forward map and a backward map, we impose the loss, almost like the way we construct the GW to invert. Although we use the forward, but we did not really impose that to be the invert of the forward process. And there are ways to do it by changing the way you write the loss. So there's a lot of interesting question there and of course, There are also other examples where the parameter theta actually is very, very meaningful. For example, if you could apply the same framework to PDEs, where the coefficient of the PDEs are physically very meaningful, and you want to estimate them, then the question is, how well can you estimate these finite dimensional parameters when you have these non-parametric terms that you are also estimating as part of the process? So there's a lot of questions that we're working on right now. I remember a student that are working on these different issues, and I'd love to also collaborate if there is an interest in the room for stuff like that. So the second part of the talk is to talk a little bit about the MCMC technique that we use to fit the model. How much time do I have? 10 minutes? Okay. The way we fit the model is using this asynchronous MCMC scheme that I'm also very excited about, and maybe take a few minutes to talk to you about. So this is a sort of a generic version of the model that I described earlier. You have some log likelihood error like this, and we constructed the prior for the parameter theta, and then this is exactly the prior that I was constructing, and you end up with a Poisson distribution of this form. The way we construct the prior here is not really important. So what we're doing here, you could really do exactly the same thing with other types of prior. Just specifically, this is the one that we use to do this. But you end up with a Poisson distribution that looks like this. And of course, if you want to sample from this, the natural thing to do is, MCMC 101 is that you fix theta, you update delta, you fix delta, you update theta. And when you fix delta, updating theta here is, you have a lot of options. When you fix theta and you want to update delta, then this is sort of a standard, Gibbs distribution where you don't have a lot of choice. You cannot do it jointly, so you have to apply some sort of Gibbs sampling to it. And the Gibbs sampling says that you have to do the update one at a time. So the idea of asynchronous MCMC is just that, when you're trying to do the Gibbs sampling for the delta, I'm going to actually do the update in parallel. Instead of updating one sequentially, one at a time, we're going to just pull out a number of the component delta that we want to update and then just update them all in parallel. So that's the main idea of it. Of course, it's very easy to construct an example where you do that, then you will not sample from the correct distribution. But the question is also that there are settings under which this actually works well. And the game is to try to find settings where it works well. So this is what I'm saying. So this is a procedure. You could do your regular Gibbs sampling, but instead of this second step, you don't do it. You actually update the component asynchronously. So here is an example where the asynchronous update actually failed. So here I have a joint distribution, P0, 0, 0, 0, 1, 1, 0, 1, 1, and I want to sample from this. I could do Gibbs sampling. So when I fix the second component, let's say I fix the first component and it's 0. I come here, I use this distribution. Then of course I had to set the second component to 1. I have the second component to 1, then I take this column and I sample from it, and then normalize it and sample from it, and that'll tell me what the value of the first component. Keep doing that. That's your Gibbs sampling. So what I'm saying now is that, well, you know, whatever value that you have at a given time, you independently pick the columns and pick the rows that you are, and then just draw a sample from it independently. And it's easy to see that when you do this, you have a non-zero probability of visiting this state 0, 0. So for example, if xk is 1, 1, that means that you know, you take this. Of course, you know, if you do asynchronous, if you independently update the two components, you have a non-zero probability that to end up in 0, 0. But of course, if you're doing regular Gibbs sampling, you will never enter 0, 0, you know, because there's no mass at 0, 0. And your Gibbs sampler will never allow you to go to 0, 0. But asynchronous Gibbs will allow you to go to 0, 0. So it's actually biased. It's a procedure that is biased. And you could calculate the bias, and it turns out that the bias is precisely how, you know, you need to look at. So when, for example, when you're trying to update the first one, given the second component, what is when you look at all the other components, how bad, so how different can they be if you start putting different things at the other component? So this particular case, you know, it's a very simple setting where we only have one other component. So I just need to compare the distance between this conditional distribution when the second variable is 1 versus when the second variable is 0. And it turns out that that's actually the bias that you will incur when you do asynchronous sampling. Another way to say is that, well, you know, 2 minutes, all right. And it turns out that in a lot of, okay, so what I'm saying here is that if you have a distribution which has weak dependence, right, where your conditional distribution, given everything else, it does not depend too much, right, on these other variables. The amount of bias that you would incur would be small. And it turns out that in many Bayesian variable selection setting, this is actually the kind of situation that you have where you can actually quantify quantities like this, and it gives you the bias that asynchronous MCMC can get in settings like that. So I'm going to skip, and we have a formal analysis of it where we show that, well, if at least in a linear regression case, if you have enough sample size, if you do asynchronous MCMC and you compare how well it recovers the true parameters, you can actually bound that. And you know, it's surprising. I mean, the method really works really well. I mean, essentially what you do is you just do your regular metropolized Gibbs, except that when you want to update the deltas, you do it asynchronously, and that's it. And so because you're doing it asynchronously, it's much faster. In terms of computational statistical recoveries, you don't lose much, and it's much better than Bayesian approximation, at least for logistic regression settings. And this is what we actually been using to do deep learning, and we are using this to train all the deep learning model that we have, and it works well. And it's the computational cost compared to stochastic gradient descent to do deep learning is essentially a matter of moving and handling these different deltas that we had to add to the model. But we are able to use it actually to train very deep models. I don't have time to present this result. I'm happy to talk about it. And so here again in this project, there's a lot of interesting theoretical questions that we're also interested in working on. Right now, we did the analysis in the linear regression case because in the linear regression case, we can integrate out the theta and then get again markup on the deltas. And then there's a co-coupling argument to do the proof, and we can do it when we integrate out the theta. But the question is, if we don't, we cannot integrate out the theta in the non-linear regression models. How to analyze this asynchronous MCMC is still unclear. We don't know how to do it, but this is the kind of stuff that I would love to collaborate on if there's any interest in the room. So I'll stop here. Thank you very much for having me. Questions?
Any questions from audience?
So I have a quick question, please. So in the first part of your talk, so there are no conditions on the forward model, but we know that for linear inverse problems, the eigenvalues of the linear map kind of plays a role in how good you can cover X.
Yeah.
But your condition seems to be only on how rich your neural network architecture is.
Yeah. Yeah, that's absolutely. Yeah, that's absolutely right. So something I didn't have time to say is that actually we assume in this result that I presented, we actually assume that we know the forward model. So we break down the problem, and the part that we analyze right now is that the forward model we know exactly. So we're not actually trying to estimate that. The only part that we're trying to estimate is the backward, the GW. That's that we estimate. But yeah, I would imagine that if we don't know, then we have to, and in that case, of course, the theta will show up in the GW because it will become GW theta, and it will be a different story.
Any other question? I have one question myself.
Yes.
And in my understanding, in this talk, you cover the situation, the data are independent RID case.
Yes.
I wonder what if the data is not RID? For example, there's time dependence.
Interesting. I had no idea. I don't have the reason is because I don't have a good time series model that I would be super excited about applying to this remote sensing data that we have. And so I'm happy to if time series model is always this thing that I feel like is not a flexible enough set of models for this really, really large data set that, and so I haven't looked into what is the theoretical properties of it.
Talk about this later.
Yeah, yeah.
Please join me in second speaker again.